Extend multi-queue scheduling algorithm, right? So today we are going to spend maybe half of the lecture on a detailed explanation of multi-queue and different scenarios of how multi-queue scheduling algorithm works. Why it has so many rules, what is the purpose of each rule, what specific type of scenario is each rule trying to address. So we'll go through that in detail today. And then after that, if we have time, we will talk about semaphore. So you have learned how to use semaphore in 252, but in this course, you need to learn how to implement semaphore. And so looking at this synchronization mechanism from a different angle. Okay. So this is the current process life stages we have learned. Right? Ready state, current state, suspended state. When a process is just created, it's created and it's created to be in suspended state. And then we call resume. Resume will put this created state process into the ready queue, and then in the future, resched and context switch will be able to schedule in this ready process and execute it. Okay, right, so this is where we are in terms of the processes life stage. Later we'll see more life stages of processes as we continue to learn more functionalities of OS, such as semaphore and messages sending and receiving. All of these functionalities will add more stages to a process life cycle. All right. So we rushed through scheduling algorithms in our previous lecture. We're going to go through it again. So motivation, right? So the reason that we need scheduling is that every process, precisely because every process has different life stages. In some life stage is executing instructions on CPU. In some other stages, it's blocked on I/O. It does not use CPU. It's waiting for I/O results. Right? And this is illustrated using this diagram. This is how a program typically executes. Right? In a certain period of time, it will execute the CPU instructions, and then it will issue a I/O operation, such as a read from file. And once this I/O operation is issued, you wait for the I/O operation to finish. And during this wait, because the process program does need to wait for this result, so it does not really use the CPU to do anything. And if we do not, if we still let this process hold this CPU, then the CPU cycles will be wasted. Right? And so that's the whole motivation of scheduling. So when this process is performing I/O, we want to schedule in some other process to do their computation. Each process goes through this cycle: CPU, I/O, CPU, I/O. And if we interleave these processes smartly, we will be able to multiplex CPU resource and I/O channel resource more efficiently. Okay. All right. We also look at this diagram. It shows that most of the CPU burst is very short, but there are longer CPU bursts. They just happen very rarely. Okay. We also explain this. Let's just quickly go through this again. Right? So, CPU scheduling decisions can be made when the process goes through these 4 stages. Sometimes when it's switching from a running to a waiting state, like when it's doing I/O, usually you want to wait for when you wait for the I/O result, you schedule yourself out. Right? So has anyone read the Xenu code and learned how this happens? In Xenu, it does perform I/O, right? When it performs I/O, it will put itself in a wait state. How does that happen? I mean, this is ahead of our lecture, but anyone looked at it, know how it's done? Okay, I'll briefly explain. In Xenu, you perform a disk I/O or remote file system operation. You use semaphore, right? You use wait. Use wait to wait for the I/O result. And when you use wait operation, you put your process into the semaphore's queue and wait for the I/O to finish. Okay. When you put your own process onto a semaphore's queue, you change the process from ready or current to wait state. Okay. So that's how how it happens in Xenu. Right? You can change from running, which is current, to wait state through this wait operation. And when you perform I/O, you call this wait operation, and wait will put your process onto the semaphore that it uses to protect this I/O channel. Okay. All right. So later you will see. But yeah, we're jumping ahead a little bit. Switching from running to ready state. Right? So this is happens all the time. Right? So whenever there is a timer interrupt, you need to check whether the current process has a lower priority or equal priority compared to the first process in the ready queue. And if so, you need to switch it out. Switch the current process and put it onto the ready list. This is switching from running to ready, how it happens. And switch from waiting to ready. This is typically happens when an I/O operation finishes and it triggers an interrupt. Okay. And this interrupt will tell the OS an I/O operation has finished. You need to check whether I need to change the process from waiting to ready, so the process can renew its execution in the future. Okay. Terminates. Right? When you kill a process, of course, you need to rescan. You need to do a rescan. Okay. And so these are the locations where scheduling decisions need to be made. Right? When you switch from running to waiting, you need to pick what is the next process to switching. Right? When you switch from running to ready, you are also picking what is the next process to switching. When you switch from a process from waiting to ready, you need to check whether this process who just finishes its I/O operation has a higher priority than the current running process. And if so, you need to switch the in to replace the running process. Terminates, right? When you kill a process, you also need to check whether you need to reschedule the running process. Right? So these are the locations where you need to make a scheduling decision. Okay. Schedule 1 and 4, these are non-preemptive, meaning that these are locations where the running process is making a decision that it wants to give up the CPU. The other scheduling is preemptive, which means that another process can interrupt the current running process. And change the current running process. Right? For example, this second scenario, switch from running to ready state. Right? This could happen in a preemptive way because it is possible the current process is running, but got interrupted by the timer interrupt. And the timer interrupt forces the switch from running to ready. And forces the current process to change from running to ready. Okay. And number 3 is the same. Right. Switching from waiting to ready, it means that there is an interrupt. Some I/O has finished. This finished I/O triggers an interrupt, and this interrupt could force the current process to be switched off. If this I/O is finished for a process that has a much higher priority than your current process.
Would the same thing happen with like the timer?
Yeah, timer is for the scenario 2. Right?
So
for scenario 2, a timer interrupt could happen, right? And they force a context switch to switch the running process to be ready.
I mean, like after a timer has ended, like a sleep, for example, going from waiting to ready. Like what?
Sorry, can I say that again?
As in, like after a timer finishes, like going from waiting, or like if you're sleeping, you want to sleep, going from waiting to ready.
Sleep is different. Sleep can only be waken up through signal, right? And when you issue signal to wake up a process, yeah, that's also where you need to make a decision whether the process that just just waken up has a higher priority, and you also need to make a decision there. All right. And the scheduling has many possible goals when you design a scheduling algorithm. You can maximize the CPU utilization. You can maximize the throughput. You can minimize the turnaround time and minimize the waiting time, minimize the response time. Most of the time, very often these goals are consistent with each other. Right? So you maximize CPU utilization, the throughput also increases. But in certain scenarios, they could conflict with each other. We talked about this example. Right? First come, first serve scheduling. It is very simple. The first process arrive at CPU will get served first until it finishes. Right? Or specifically in this example, until it finishes its CPU first and give up its CPU. Right? It is possible process 1 uses the CPU for processing for this amount of time and give up the CPU to do I/O and then come back later. Okay, this is just representing the CPU burst of each process. Okay, in this example, first come, first serve scheduling will serve P1 first, P2 second, and P3 last because they arrived in this order. But the waiting time, obviously, for P2 and P3 is very bad in this case. So the average waiting time will be 17, which is not very good number. So if the process arrives in a different order, P2, P3, P1, you will have a better average waiting time, right? Because P2 and P3 just has a very short CPU burst and finishes very quickly. Okay. We explain this in our previous lecture too. This is where we skipped. Right? I think we did not discuss this. Shortest job first scheduling. It is a strategy designed specifically to address the previous problem. Where you have a long job blocking a bunch of short jobs because you are using first come first serve. Okay, so in using shortest job first scheduling, you associate with each process the length of its next CPU burst, and use this length to schedule the process with the shortest time, or the shortest CPU burst. Very intuitive idea. Shortest job first is optimal. It gives a minimum average waiting time for a given set of processes. This is very intuitive, but the difficulty is that how do you predict the CPU burst for each process? It's hard to predict. Or in theory, predicting the future for a program's execution is undecidable. It's equivalent to the halting problem. So in theory, you cannot predict it accurately. So the difficulty is to predict the length of the next CPU burst. But you can ask the user, you can use the recent, for each process, you can use its recent history to predict its future. People do that, and usually that yields pretty good results. Okay, so people do implement shortest job first scheduling algorithm using certain types of prediction of the future. Okay. All right. So this is example to showcase the shortest job burst, assuming that we know the CPU burst of each process. P1 has a burst time 6, P2 has 8, P3 7, P4 3. And if they arrive at approximately the same time, then we use SGF to scheduling them. We will schedule P4 first, right, because it has the shortest burst time, and then P1, and then P3, right, which has 7, and then P2, which has 8. Very intuitive. Okay, so the average waiting time is 3 plus 9 plus 16 plus 0, right? P4 did not wait for anyone. Okay, average waiting time is 7. Okay. So this is one example how people use the history of execution to predict the future CPU burst. And in many use cases, people do use this algorithm. So, yeah. So the difficulty of SGF is that you need to predict the future. You need to estimate the length of the next CPU burst. Right? The idea is that the next CPU burst might be similar to the previous one, right? And people build solutions based on this approach. And then you pick the process with the shortest predicted next CPU burst. And this is the formula people use to predict the length of the next CPU burst. So they use exponential averaging. So in this case, Tn is the actual length of the nth CPU burst. Tau n plus 1 is the predicted value for the next CPU burst. And then Tn is calculated using this formula. Sorry, this is tau n plus 1. There's error there. Right? This is not tau n equal 1. This is tau n plus 1. Right? Is equal to Tn, which is the CPU burst in the previous time slot, right? Plus this is the prediction that you made for the previous time slot. The previous CPU burst, this is prediction. And you use them to predict the next CPU burst. Okay, so there is a preemptive version of it. It's called shortest remaining time first. But this is an example of how the algorithm works using this prediction, right? Using this algorithm to predict it. Okay. The specific algorithm that is used here to do the prediction is not that important. Right? People have developed different versions of prediction. The idea is similar. They all use the recent history of the previous CPU burst to predict what will be the next CPU burst. The idea is very simple. This is just an algorithm to showcase how this idea can be implemented. But there are a lot of algorithms implementing similar idea. So this is an example to show how you do the calculation. We won't go through it here, right? We won't spend more time on the multi-queue algorithm. Okay, so another example, shortest remaining time first. Okay, so this is not shortest job first algorithm anymore. Right? This is shortest remaining time first. The difference is that we are not assuming the jobs arrive at around the same time anymore. Okay. In the previous shortest job first scheduling algorithm, you assume that the set of jobs arrive at approximately the same time. But here, P1 arrive at time 0, P2 arrive at time 1, P3 at time 2, P4 arrive at time 3. Okay, and because they arrive at different times, so the theoretical guarantee using shortest job first algorithm does not make sense anymore. Okay. And the intuitive idea is that we use the shortest remaining time first. Right? So when P2 arrives at time 1, it knows what is the remaining time of P1, which is 7. Right? If P1 executed starting from time 0, its remaining time is 7 at time 1. And it compares 7 and 4, which are the remaining time of P1 and P2, and decide which is the one that needs to be scheduled. Right? In this case, it decides P2 needs to be scheduled at time 1. Right? Because it picks the one that has the shortest remaining time. Okay. Similarly, right, when P3 arrives, when P4 arrives, you also make this decision. Okay. This is still very straightforward. Anyone want to try to explain how? I already explained how it works for P1 and P2. Anyone want to try to explain how it schedules? Make decision in the later scheduling point. Yes?
There's like 7 seconds remaining of P1, so it picks P4 first because it only has 5.
Mm-hmm. But before that, I think there is another decision need to be made, right? When P3 arrives at this point, at time 2, what happens?
In that case, P2 had at time 2, so then 3 seconds remaining, whereas P3 is arriving with 9 seconds remaining, which would be long.
Exactly. Right. So at this point, right, whenever a process arrives, you need to make a scheduling decision. At this point in time 2, P3 arrives, it has remaining time 9. And P2, it has executed for like 1 second, so it has remaining time 3. And P1 has been scheduled out, it has remaining time 7. Among these 3, P2 still has the shortest remaining time, so it keeps running P2 until it finishes. When it finishes, it checks, then at time 3, P4 arrives. Okay. At time 3, P4 arrives, and that's when it makes another scheduling decision. It says that P2 is still the one that has the shortest remaining time, so it will continue executing P2 until it finishes. When it finishes, that's when it looks at the remaining processes again and see which one has the shortest remaining time, and it picks P4 because it has the shortest remaining time 5. Okay, so this is how shortest remaining time first works. Okay, and its limitation is similar to shortest job first. You still need to predict what is the next CPU burst for each process. Okay. Yeah. So priority scheduling, right? So you have a priority that you assign to each process, and the CPU is allocated to the process with the highest priority. This is slightly different from shortest job first or shortest remaining time first, where we don't have a priority for each process. We just take a look at who has the lowest shortest remaining time. We schedule it first. It's like their priority is decided dynamically, okay, without a priority number. But very often, like in Xenu and in Linux, you will see that every process has a number. In Xenu, it's a priority number. In Linux, you could see that people call it a nice number, NICE. But they are essentially priorities associated with each process. Okay, and a CPU is allocated to the process that has the highest priority. And you can have preemptive, and you can also have a non-preemptive scheduling. Different OS does it differently. Okay, and shortest job first is a priority scheduling where priority is the inverse of predicted next CPU first time. The problem with priority scheduling is that it could cause starvation. The process that has the highest priority will have the CPU. If in a very unlucky scenario, you have some process who happen to always have the lowest priority, then it can get starved. Right. A solution is aging. Right? As time progresses, you increase the process, some process priority. Another simple strategy is round robin. Right? So each process gets a small unit of CPU time, 10 to 100 milliseconds, and after the time has elapsed, the process is preempted and added to the end of the ready queue. Okay. So this is also already implemented in Xenu. Okay? So once every process finishes the time slice, if there's any process that has equivalent or higher priority, the current process is added to the end of the ready queue. Okay. All right. Okay. So this is a simple example, right, of round robin with time quantum equal to 4. So you have a P1, P2, P3, and each of them will be scheduled for milliseconds. P1 gets 4 milliseconds. P2 gets 3 because after 3 milliseconds it finishes, it's a CPU burst. So it schedules itself out. Right? And then P3 has 3. And then P1 is scheduled in to execute for 4 milliseconds, and then P1. The remaining time is just P1. Okay? Right. So typically it has a higher average turnaround than shortest job first. Shortest job first is still the theoretical best scheduling policy, but round robin could have better response. Okay. All right. Time quantum and context switch. In Xenu, I guess everyone has read the code, might know there is this data number called quantum. Right? So have you seen this data number quantum? Right? It is the time slice each process can execute before the next timer interrupt get fired, and it might need to perform context switch. Right? Quantum. So essentially, after every time quantum, you need to check whether a schedule has to be made. So you need to check the readiness, see whether there is another process that has higher priority or equal priority to your current process, and you need to do context switch. Okay. So if you have a very high quantum, okay, it means that given this quantum, before this quantum is exhausted, you are essentially disabling all the timer interrupts. Okay, so during time from 0 to 10 milliseconds, there will not be any context switch because you are essentially disabling all the timer interrupts during this quantum. Okay, so if quantum is 6, it means that at time 6 you might do a context switch if there is another process that has equivalent or higher priority. Right. If quantum is 1, it means that you might be doing context switch very often, every 1 millisecond, and there is a trade-off here. Right. Context switch itself is not very cheap. It costs resource. You need to perform timer interrupt execution, and you need to store the old process state. You need to load the new process state. Right? Context switch is not free. So performing very frequent context switch is not ideal. But on the other hand, if you use very long quantum, it means that one process can hog the CPU for too long. And it makes the round-robin scheduling algorithm not efficient. Okay. Yeah, so there's a trade-off here. Okay, so your turnaround time can vary with the time quantum. So if you have every turnaround time, it's affected by the time slice. So the empirical decision people made is that if you have about 80% of the CPU bursts shorter than your quantum time slice, then you have a pretty good result of using your scheduling algorithm. Okay, so that's how people select this quantum. Right? You can profile the programs running on your on your computer and check their CPU burst duration and make sure your selection of quantum is longer than 80% of their CPU burst. Okay, multi-queue. Now let's go through this slowly with examples, right? We're using the other slides that we have. 1 second. Okay, so this is a slide that's from the textbook that I recommended at the very beginning of this course, right? Operating system 3 easy PCs. I still recommend people who have time to read it. It's an enjoyable read, I would say. So it's one of the textbooks that is actually a quite enjoyable book to read. Okay. All right. Multi-level feedback queue. In this slide, we will showcase a few examples to motivate why each of the roles in multi-level feedback queue is designed. Okay. We want to show that we don't just want every student to remember how to design this queue, but we hope that you also understand the motivation behind each role. Okay, so this multi-level feedback queue is a scheduler that learns from the past to predict the future. Most schedulers try to do this, but multi-level feedback queue achieve this goal is very simple design. Okay. The objective is to optimize the turnaround time. You want to run shorter job bursts and minimize the response time without prior knowledge of job length. Right? We don't have the CPU burst time. Okay. Multi-level feedback queue has a number of distinct queues, and each queue is assigned a different priority level. And a job that is ready to run is on the same queue. A job on a queue with higher priority is chosen to run. And the jobs that have the same priority will be scheduled using round robin. We explain this. These two rules are very simple. Okay. So they are very intuitive. Okay. So now the later rules are more interesting. Right? So multi-level feedback queue varies the priority of a job based on its observed behavior. Try to predict the job's future. So for example, if a job repeatedly relinquishes the CPU while waiting IOs, keeps its priority high. We explained this briefly in the previous lecture. It means that a job finishes its execution very quickly and give up CPU, wait for IO. This is a behavior This is a behavior that indicates that this process typically has a very short CPU burst. Does that make sense to you? Remember, the whole point of multi-level feedback queue is to use past to predict the future. Okay. You want to predict the future CPU burst of a process. If a job, a process, repeatedly give up its CPU and then go to do I/O, it means that it did not finish using its allocated time. Okay, let's pause here. I think a little bit, right? So I hope that everyone understands the rationale behind the design of each rule instead of just go ahead and implement the rule. Because these rules are multi-level feedback queue, and the rules are extremely simple, right? If you just want to finish a lab, it's very easy, okay? But for most of the designs in OS, for most of the designs in OS, they are straightforward if you know how to implement it. The point, the difficulty is the rationale, right? How did the people come up with, right? Why it needs to be implemented like this? 1 second. Increase the battery. So I hope everyone can get the rationale behind each rule, right? So the first one, a job repeatedly relinquishes the CPU. What does this mean? In Xenu, right, to make it concrete, in Xenu it means that, remember each process has a quantum, its time slice, allocated to it before the timer interrupt can schedule it out, right? In Xenu, it means that before a process finishes using its quantum, it voluntarily gives up the CPU. Schedule itself out because it's doing I/O. It means that it did not finish using its allocated time, and it gave up the CPU. And this happens very frequently. This means that most of the time, its CPU burst is very short. It's shorter than the quantum, than the allocated time slice. Okay? All right, so this is how you predict the future in multi-level queue, right? So if a process repeatedly give up CPU before it finishes its time slice, it means that its CPU burst might be very short. Because its CPU burst is very short, remember what is the goal? The optimal algorithm is shortest job first, right? The optimal scheduling algorithm is shortest job first. Because this process has a very short CPU burst, so in the future, we probably want to schedule it to have higher priority. Okay? So that's the rationale behind why this kind of job we want to keep its priority high. Does that make sense? Okay. Yeah, if you just look at the rule, you might not get why it's designed like this. I hope everyone know why it's designed like this. If a job, on the other hand, right? So if a job uses CPU intensively for longer period of time, it means that its CPU burst is very long, right? Reduces priority. If its CPU burst is long, reduces priority. This aligns with shortest job first, the optimal algorithm. In shortest job first, it means that the long jobs, which means that the process has a long CPU burst, should have lower priority. They are scheduled later. Okay. So these two rules, they are essentially trying to mimic shortest job first scheduling algorithm by using the history of this process's CPU burst in the history to predict its future CPU burst. Okay. I hope this makes sense. Right? So yeah, let me know if you have any questions. The rationale is more important than the rule themselves. The rule themselves is straightforward. Okay. All right. But we'll see that these two simple rules, they are not sufficient. They can have problems like starvation. They can be gamed. A user can design their program to game this strategy to make sure that their own program always has the highest priority. Right? So later rules, the other rules are designed to fix these problems. Okay. Yeah. So later rules, right? When a job enters the system, it's placed at the highest priority. So this is simple. You don't know you don't have a history of this job. So you just optimistically trust that this job might be urgent. It might have a short CPU burst. Let's give it a try first. Okay. If a job uses up an entire time slice while running, its priority is reduced. Right? This rule 4. Rule 4a is designed following our previous intuition. Rule 4a is designed following this rule, right? This example. Okay. All right. Rule 4b. If a job gives up the CPU before the time slice is up, Yeah. Rule 4b is designed following the first example. And rule 4a is designed following the second example in the previous slide. If a job gives up the CPU before the time slice is used up, it stays at the same priority level. Okay. It has high priority. If a job uses up an entire time slice while running, its priority is reduced. It means that this process, its CPU burst is long. Okay. So this is how multi-level feedback queue approximates shortest job first. All right, now let's make it more concrete. Let's look at the examples. Okay, so in this case, we have one job that is long running. Right? When it enters the system, it's given highest priority, is put in Q2. And after it finishes the current time slice, right, because it's a long running job, it does not give up the CPU voluntarily. Right? So after time slice is used up on Q2, its priority is decremented and is moved to Q1. And because there's no other processes running in the system, so it still gets the CPU and run until the time slice is used up, and then its priority is decremented again, and takes the user CPU to continue running until the end. This is the simple case. All right. Okay, so this is another example. It's also very simple. You have two jobs. Job A is a very long-running job. Suppose it came into the system a long time ago, so its priority was already dropped to the lowest. Right? And job B is a short-running interactive job. It's very short. It's just 20 milliseconds. Right? And so when A is running, B arrived, because B has a high priority, so it will interrupt or preempt process A. It will take over the CPU, CPU will be assigned to process B, and process B will execute for a time slice, and its priority is reduced to Q1 and got another time slice until it finishes. Right? It only has 20 milliseconds, so it finishes execution. And then the system switches to execute process A. This is still very, very simple. Okay. All right. What about I/O? Right. In this case, we have a slightly more complicated example. Job A is a long-running CPU-intensive job. Right. You can see that it has already dropped to the lowest priority. Its interval, right? So the duration for its CPU burst is also longer. This blank in between its CPU burst, you can consider them doing I/O. Right? So this blank in between their CPU burst is I/O burst. Okay, so you can imagine, right? So these black bars show that the process A has a long CPU burst but a very short I/O burst, while process B has a very short CPU burst but a long I/O burst. Okay. All right. So in this way, because can anyone try to explain why the scheduling look like this? Why? Yeah, I think this becomes more interesting. I'll give you 30 seconds. Okay. So why does the scheduling of this process A and B look like this? Okay. Anyone want to give it facts?
Just because he never uses the whole 10 milliseconds, it never gets decremented in priorities.
Exactly. Right. It's also very simple following the rule, right? Because in this case, process B CPU burst is very short. It never uses up its CPU allocation, its time slice. Because it never uses up its time slice, so its priority stays in Q2. And process A, because its CPU duration is much longer, so it always uses up its CPU time slice. And, so that's how its priority drops to Q0. Okay, so this is how multi-level feedback queue keeps an interactive job at the highest priority. An interactive job usually uses CPU very shortly and then spends more time performing I/O. Okay. Yeah. But this also shows you that the current version of the multi-level feedback queue can be gamed if you design your program to be like this, to run like this, very short CPU burst. It doesn't even need to be short. You can design your program to use 99% of the time slice and then give it up. Right? That way you can keep your process in the highest level. Okay? Right. So these are the downsides of the basic version of multi-level feedback queue. Right? Starvation. If there are too many short burst jobs, right? So interactive jobs with short CPU bursts, then the long-running jobs will never get any CPU time. They will be stopped. Okay. Second is that you can game the scheduler if you design a program that uses up 99% of the time slice, then do I/O. Right? And this job will get a much higher percentage of CPU time. And another downside is a program may change its behavior over time. If you have a process that performs long CPU burst in the beginning, but short CPU burst later, then it's going to suffer. Because during the first period of time where it performs a long CPU burst, its priority is gradually dropped to the lowest priority. And then after that, even if it has short CPU burst, it cannot be promoted. Okay? Right. So that's why we have a limit for multi-level feedback queue. So rule 5. After some time period S, move all the jobs in the system to the topmost queue. Kind of refresh. Okay, so example, we have one long running job A with two short running interactive job B and C. Okay. All right. Without rule 5, this is what happens without rule 5. Okay, this is what happens with rule 5. I'll again give you 30 seconds to look at it and try to understand it. If someone wants to explain it, that would be great. If not, I'll just go ahead and explain it. But 30 seconds. Think about how scheduling happens like this. The left side is without rule 5. The right side is with rule 5. Okay, anyone want to try to explain? So do you one at a time, right? On the left hand side, without rule 5, why the schedule look like this, and what is wrong with it?
So without rule 5, the really long running process will hit all the time place, so the priority is going to keep decreasing. And then when the two short running jobs one, they don't pick up the time place, so they always stay with high priority. As it keeps moving back and forth, it's only going to be picked up the CPU. And if you're still running the longest running
Exactly, right? It starts the long running process. Right? Yeah, so that's what happens on the left side, right? So in this case, we have a A, which is a long running job, a long running process with a very long CPU burst, right? Because it has long CPU burst, so the priority, it uses up every time slice, and its priority drops to the bottom, right? And when at this point, the two short running job or two interactive process arrive, each of them have very short CPU burst. And because they have very short CPU burst, so their priority will always stay in the highest queue, in Q2. Right? So that's why the CPU allocation look like this, starting from this point. When B and C arrives, they will hold the CPU forever because their priority stays in Q2. And job A will never get scheduled. Okay, so this starts job A. Now, on the right-hand side, with rule 5, things change. Right? Anyone want to give a highlight with how things change in rule 5? I think it's a straightforward following. Yes. Exactly, right? So this is where the entire system is refreshed. All the items in every queue is moved to the top queue. Right? The job A uses up time slice in Q2, Q1, Q0. In reality, this might stay this job A, this refresh interval should be longer than this, right? So job A will stay in this lower Q0 for a longer time, and then at this point in time you refresh, which means that all the processes, in this case process A, will be moved to this point. Okay, and this happens periodically, so that's why when B and C, when these two jobs arrive, they will not be able to start A because although their priority stays in the high queue, but job A still get a chance to be moved to the highest queue. Okay, and it gets moved to the highest queue, and it has the same priority as B and C, so it gets scheduled in a round robin manner in the topmost queue. Okay, yes.
If S is like constant, then how come like the time between the boosts is like different? Like it gets like wider, the space between.
Yeah, it's just drawing, right? So it
doesn't matter.
It doesn't have space. Yeah.
But it's still a length of time S, right?
Yeah. It doesn't have enough spaces. Yeah. So usually this period of time where you do this refreshing should be much longer, right? So it won't be this short. Okay. So this rule 5 is to solve the previous problems: starvation, gaming the scheduling algorithm. Oh, sorry. The rule 5 is just for preventing starvation. We changed the rule 4 slightly to prevent gaming. Okay. So yeah, change to prevent gaming. Right. So we rewrite rule 4A and 4B. Once its job uses up its entire time allotment or time allocation at a given level, regardless of how many times it gives up CPU, its priority is reduced. Right. This is also simple, trivial to understand. Right. So you can imagine, suppose I allocate a time slice, in total time slice for a process at Q2 to be 200 milliseconds. When this process uses up this 200 milliseconds in a cumulative way, so it might give up this 200 give up the CPU after 100 milliseconds, but we remember that. We remember it has used up, has used the 100 milliseconds. its remaining time slice is 100 milliseconds. Okay. We remember that next time it's a scheduled back, a continued execution, it will keep using its remaining time slice. Okay. When it finishes using its allocated time slice at this level, at this 200 milliseconds, it will get decremented to the lower queue no matter what. Okay? So this is slightly different. In our old design of Rule 4, a process will stay in the same queue if it gives up CPU before it finishes using its allocation, the time slice. Okay. But now we changed it. A process, for each process, will account for how much time it's spent in this queue, cumulatively. Okay? So you can imagine it's like in the old version of Rule 4, a process gets refreshed 200 milliseconds or time slice every time it gives up the CPU. Right? Every time it gives up CPU, it gets refreshed time slice. That's the old design. But in this new design, you don't get refreshed time slice. You only have one time slice allocated to you. When you use it up, you go to the lower level queue. Okay? So this is how it looks like. So I'll give 30 seconds to think about this. Right? So without the new Rule 4, with the old Rule 4, the scheduling happened like that on the left side. With the new Rule 4, the scheduling happens on the right side. Okay? So I'll give you 30 seconds, and maybe someone could try to explain both of them. This, with the previous practice, I think this one should be easier to explain. Okay. The left-hand side is using the old Rule 4A and 4B to do scheduling. The right-hand side is when you use this new Rule 4 to do scheduling. 30 seconds, let's wait a little bit. Yes?
Yeah, so.
Sorry, the one in the back. Yeah,
Yeah, so the one on the left side, it's giving up its CPU time early, and it's staying up in the higher process, it's gaming the system. And then on the right side, after after the first process, even though it's given it up one time, after the second time that it comes back to its cycle, it's like, since the CPU is able to like retain memory of how much time it's already taken up, and it's exceeded the time allotment, it goes down prior to the
Exactly.
next time.
Exactly. Right. So, yeah, just quickly reiterate what he said. Right. On the left-hand side, using the old rules, this process is gaming the system by using the allocated CPU time slice 99%, right? 99% of it, and then give it up voluntarily, and then when they give up the CPU voluntarily, it will get a refresh time slice. Its priority is stay the same. It's going to add it to Q2, which means that it gets a renewed time slice. So next time it's scheduled, it's still in Q2, it can still use a 500 millisecond time slice, and it uses let's say 190 milliseconds out of these 200 milliseconds, and then give up the CPU. Because right, the old rules will see that because this process voluntarily give up CPU, it stays in the same queue, so this process is added to Q2 again, and will stay in Q2 forever, even though it's using much more CPU than other process. Okay. Now, using the new rule 4, because the OS right now, it remembers the accumulated CPU time used by each process, right? So this process might be trying to give the scheduler, but so it uses 190 milliseconds out of the 200 milliseconds, right? But because the OS remembers it has 10 milliseconds remaining for its time in this Q2. So next time when it's scheduled back, after it finishes its 10 milliseconds execution time, it will be decremented. So the scheduler OS will say that you have used up your time slice accumulatively, right, in Q2, and it will be decremented to Q1. Okay, so this is how it gets decremented to Q1, and then the same thing happens is decremented to Q0, and then in this way it cannot game the system and get more CPU than the other process. Okay. All right. All right. So there are some other adaptations of multi-level feedback queue. Right. This is another example. If you have a lower priority, you have a longer quanta. Right. So if you have a higher priority, you have a shorter time slices. Right. So essentially, we are saying that I can give you higher priority, but because we are assuming the process that has higher priority should have a shorter CPU burst. Right? Because of this, we give the processes in Q2, we give them shorter time size. And for process in Q0, we give you lower priority at Q0 because we think this is a process that has longer CPU burst. Right? For this process has longer CPU burst, we give them slightly longer time slice. Okay, so this is some other adaptations people have tried for multi-level feedback queue. Yeah. You can try this for your own implementation too. Okay. These are adaptations or parameters that you can play with for multi-level feedback queue. But tuning these parameters to get a scheduler that works well is not an easy job. Okay, right? And because it's actually workload dependent. Right? Different workloads, different scheduling strategy work well for different type of workload. Okay, right? And actually, an intuitive idea you might want to apply, you might think would work is what if we apply machine learning technique? Right? Machine learning technique can learn patterns of the workloads, and it might be able to tune these parameters adaptively based on the workload pattern, right? Which people have done it at high level, right? People have done it at cloud system level, but you cannot afford to do it at CPU level because the CPU scheduling decision is very fast, and using machine learning to make the decision is just too slow. Okay. Right. So these are some other implementations. Right? In Solaris OS, you have multi-level feedback queue implementation, and these are the parameters that they set for multi-level feedback queue in Solaris OS. Okay, and the user and the system admin can provide hints, right? Like nice value, really nice this value for problem, for process that they think are more important. Okay. All right. So these are the rules of multi-level feedback queue, and I assume that everyone has already know that these are rules, and you need to follow these rules in your implementation for Lab 2. Okay. Okay, I think that's it for today. That's a detailed explanation of multi-level feedback queue.